Sure. Yeah, welcome to my talk, everyone. My name's Luke Rawlence, and I'm a data scientist at AMI, and I focus on working with natural language processing. Yeah, welcome to the talk. It's a very hot day, but I hope we can all get through it. I'll try not to make it drag on for too long. So the aim of this session is to identify some popular applications of natural language processing, just to make the concept of NLP a bit more real. Then we'll introduce an approach to solving natural language problems. Then we'll implement this approach to create a sentiment analysis model on real-world data set, just to break it down. So we'll start with the applications. So natural language processing is a hugely popular area in machine learning with a broad range of applications that we interact with on a daily basis. So first example is Google. Now Google has information retrieval, so it will try to access results that are most relevant to your search query, and it also has, as we can see here, kind of predictive text where it will try and complete the sentence you're typing for you based on the sentence that's most likely to be true. We have virtual assistants, which is kind of a extension of search engines where we can talk to them and they will interpret speech instead of text. And yeah, this is a lot easier way of accessing search, and also comes along with a lot of other features. We also have machine translation. So these days, machines are somehow able to effortlessly translate between different languages. And yeah, this is hugely powerful, and the impact of this is amazing. And the results have been improving year on year. And yeah, at this stage, this makes tourism a lot easier. And yeah, the implications are huge. We also have chatbots, which Ellen is familiar with. On this example on the right, we can see a chatbot where you give it the command to check stock, and then it will ask you a series of questions. And this is in the context of shoes, and it will basically filter down your results based on the answers you give. And this will give you a kind of result at the bottom based on the stock level of the shoe you want. And finally, well, second from last, we have classification of text. So this is in news articles. We can split into food, sports, politics, and this relates to news digests. If you want to kind of filter by different themes, or if you want to be suggested different news based on your interests, this is quite popular. And finally, we have sentiment analysis, which we'll be going into a bit more later, but it has huge applications. We have customer service. So for example, a call center manuscript could be automatically analyzed to see if your feedback for a product is good or bad. We have product reviews like Amazon, where you want to automatically kind of track if your product's doing well. And we have Twitter hashtags, where you can kind of track how people feel about different topics, different people, different events that are happening in the world. So I hope that puts NLP into context and the broad applications that exist for it. So yeah, now we'll be moving on to solving NLP problems. And yeah, so a kind of traditional approach, maybe the most easy to think of approach to NLP would be to just use rules, right? So in the context of sentiment analysis, you could make a list of all the positive or negative words in the English language. You could count the occurrence of these words in a given text, and then you could calculate the ratio of positive to negative words. And that would look something like this, maybe. So we have a movie review example here. The movie was bad, some moments were cool, but the overall experience was generally negative. So following this procedure, we could highlight the sentiment words. So we have bad, cool, and negative. So we have one positive word, two negative words, which means 2/3 of the words are negative sentiment, which means we can make some sort of conclusion that the article is the majority negative, and yeah, we would classify that as negative sentiment. However, in reality, this approach doesn't work so well because natural language processing is a complex task, and this is mainly due to the fact that language is not as clean cut, and especially in the English language, there are many ambiguities and inconsistencies, and the meaning of words can change within different contexts. So we need to use a more sophisticated solution, basically. So examples of how English is difficult to handle would be the concept of negation, where in the example, that was not a very good experience. If you were using rules to register sentiment, the word not would actually invert the sentiment. So
has anyone else just lost sound?
Very hard to register on a machine level in an automated system. So this is kind of what we're left with. We have the expectation that these rules are powerful. We have this nice NLP cake, and then in reality, when you deploy it, you kind of get a mixed bag of results, and yeah, it's not what you thought it would be. So this is why NLP is hard, basically, to put it quickly. So as I alluded to before, we need a more sophisticated way of solving NLP problems, and machine learning rationally is the solution, because that is where a lot of the computational performance and power that we're experiencing comes from. So this allows us to create a model that is capable of understanding greater levels of complexity and should therefore result in higher levels of accuracy. So the traditional approach of natural language processing can kind of be split into 4 sections. However, the last 2 sections are kind of agnostic of the task, training and evaluating models. So the first 2 are kind of what we're going to be focusing on in this presentation. So firstly, we have text pre-processing, which is the manipulation of text to put it into a kind of easy to read format. Then we have word embeddings, which is where you actually translate words into numbers, which can be called vectorization as well. And yeah, training and evaluating the model based on this data comes after that. So text processing is essentially a toolkit that we have, and these are kind of the most commonly used techniques within that domain. So firstly, we have tokenization, which is kind of a staple. In many cases, it has to be done in order to allow the other computations to happen. So we would start with the text. Natural language processing is fun, and then it would split into individual tokens. So the whole continuous set of text would be split into its respective components. We then have lemmatization, which is where we reduce each word to its lemma, which is a form with no inflections. So in this example, the word processing would go to process, and the word cat would go to cat, and kind of all of the variational endings of words will be reduced, so it's kind of in a minimum form in theory. We then have stop word removal, where we remove words that are commonly occurring in the English language but don't really provide any meaning. So the word is in this sentence, if we're training a model, it's unlikely to help train, so it's kind of considered noise. So we would essentially remove this through checking the text against a dictionary of words that are deemed like unuseful. Then we have n-grams, which is where we essentially join words together that frequently occur together. So in this context, we would have natural language processing as one kind of token, and then is fun afterwards. And the idea behind this is you can kind of represent concepts that have more than one word, where the words kind of need to be together in order for you to actually understand what it's trying to say. For example, natural language processing is itself a concept. So that's text pre-processing. So the idea of that is to set us up for word embedding now. So word embedding is a collective name for a set of natural language modeling and feature learning techniques in natural language processing, where words and phrases from the vocabulary are mapped to vectors of real numbers. So this is important because computers can't read, to put it simply. So when we see words, computers see question marks. So we need to solve this problem now. So a first initial method we might have for solving this problem would be something called count vectorizer, where we essentially have a table where each column is all the unique words, and for each row it would be each document, and there is a count of each word that occurs in each document. So natural language processing is fun, would be a series of ones in columns that correspond to those words. Then this movie is the best movie. It would be a series of counts that correspond to the words that occur in that document equally. So for example, there's a 2 in the column that says movie because there are 2 counts of that word. So this is a very simple way of performing word embeddings or vectorization. And this is referred to as a bag of words model because the contents of a document is represented without taking the order of words into account. We can build on top of the count vectorizer representation by performing an operation called term frequency inverse document frequency, which is essentially where we times the term frequency by a weight, which is proportional to the significance of a word in a set of documents. So yeah, I'll go through the maths of that in a minute to make it clearer. But the benefit of this method is essentially that words that are more useful in differentiating documents tend to be drawn out and multiplied by higher amounts, so they can be seen more visibly by a machine learning model. DFIDF, yeah, is especially useful in information retrieval and topic modeling. So in a Google search, when you enter a series of terms, for example, it would weight the terms that are more important when you're performing your search, and also topic modeling, because as I mentioned before, it makes it easier to differentiate documents. So an example of the maths of TF-IDF, it's quite simple. We just multiply the count by the weight. So words that are likely to occur very frequently within documents, like the word is, would be weighted very low, and words that occur not that often in documents, like the word language maybe and the word processing, would be weighted high to try and like amplify the words that are likely to be more useful. So a problem that arises with this type of word embedding is that it forms a thing called a sparse matrix, which basically means that most of the data that we're storing is zeros. And this is extremely kind of inefficient to store in a conventional fashion. So in this table we see here, we have all our documents, which are the rows, and we have all our words, which are the columns. So for example, in this text here, we have many columns corresponding to many words. However, only 5 different words occur in this text. So we would have a 1 here, and we would have 4 other ones. And yeah, we can see a lot of zeros, and yeah, this is not efficient, basically. So to break down the maths, if we have a matrix, which is 10,000 columns and 2,000 rows, then our dimensions are, we would have 20 million different values in that matrix. And if each document contains an average of 50 different words, then we would only have 10,000 values that are non-zero values. And if we calculate 100,000 as a proportion of 20 million, then what we're basically seeing is that only 0.5% of the values are actually useful, are actually non-zero values. So that is to try and show the significance of the problems of sparse matrices in a conventional manner. So we need to think of a better way of storing all this information. So this is a problem that's commonly occurring in natural language processing, and the solution that is often used is this format we can see here. So instead of storing all of the values, we only store the locations of the values that aren't zero values, which is a compressed format, and we would be storing a lot more useful information. So I introduced to you Count Vectorizer and TF-IDF. However, there are many more natural language processing methods which are getting more powerful by the day. But in this session, I wanted to introduce to you the more fundamental concepts. So some examples of more later methods would be word-to-vec, recurrent neural networks, and transformer models. And it seems that many of these methods are applying more human intuition into how they interpret text, which is making it a lot more powerful. So in this example here, we have a recurrent neural network, the kind of basic logic that is executing. And this method will essentially read a sentence, one word at a time, from beginning to end. And unlike the bag of words model, where words are represented individually, regardless of their ordering, in this method, the meaning of a word will actually be affected by all the meanings of the word before it. So this is the perfect example of how we would solve the problem of negation, where the word not would invert the sentiment of a sentence, right? So in this model, if the word not occurs before good, then in theory, the model will understand that negation has occurred, and we can therefore train a better sentiment model based on this information. So that's the kind of meat of the presentation in terms of the technicalities of natural language processing. So now we'll be going through some standard machine learning methodologies, and then we'll be going through the code after that. So this is likely to be very familiar to some of you. Once we have the data set that we've created through embedding the text, we can split this information into a train set and a test set, which is maybe 70% train, 30% test. But in our data set we have is 50-50. And then we would use the train set to train the model and the test set to evaluate the model. We also need to choose a machine learning algorithm to execute the training. So there are a number of algorithms that are successful in NLP tasks. For example, naive Bayes, logistic regression, random forests, and neural networks. In the context of supervised learning, at least, which is what sentiment analysis is. I've chosen random forests because they seem to work well with the tasks I've done, and yeah, they're quite easy to use in the context of an introduction. So moving on to evaluating a model, a very conventional way of doing this is through analyzing something called a confusion matrix, which very simply records the actually positive and actually negative results against the predicted positive and predicted negative results. And we can generate a variety of metrics using this matrix. So normally we would look at accuracy, which is the amount of correct results divided by all the results. But the confusion matrix enables us to unlock a little bit more specificity with our results. So we have a metric called precision, which is the true positives divided by the true positives plus the false positives. So that would be the amount of correct predictions out of all positive predictions. So that would basically tell us, given a result is predicted positive, what is the probability of it being correct? And then we have recall, which is true positives divided by true positive plus false negative, which is out of all of the answers that are actually positive, how many of them are predicted as positive? And we also have F1 score, which is a kind of hybrid metric between precision and recall, which gives us a little bit more insight as well. And we would prioritize different metrics based on what we're trying to achieve with our model. For example, maybe if your model is detecting tumors for cancer, you wouldn't want it to give results that it says are true that aren't, because it's quite a sensitive topic. However, if you have a model that's maybe doing sentiment analysis, you might want it to catch more results at the expense of those predictions being always correct. Some popular Python libraries for NLP, we have Natural Language Toolkit, Spacey, Gensim, Pattern, Scikit-learn, TextBlob, and Core NLP. And for deep learning, we have TensorFlow and Keras and PyTorch. In the code we're about to see, I use NLTK and I use sklearn as well. Yeah, many of these are very user friendly, so you can kind of get hands-on with them, and that's a real benefit of using Python for machine learning. And also, I will be sharing these slides if people want to see them. So we have some links here which we can see. We have a really cool lecture series from Stanford which talks about NLP and deep learning. It has 20 episodes and it's really good. I've been through a bunch of it. We have natural language processing specialization, and we have this cool website, Papers with Code, which enables you to browse the state-of-the-art applications of NLP. So that was my technical segment. I suppose we can have a little break for questions here, if anyone has any. And I'll have a drink meanwhile.
Yeah, I think the only question we've had so far is one you've literally just answered, actually, which was where there are some libraries, etc. But yeah, if anyone's got any questions, feel free to just jump on the mic now. Just somebody talking? I think I can hear something in the background.
Yeah.
Oh, there we go.
Now.
Yeah.
So I was just asking Luke that I was starting to work something on word embeddings, and this has really given me some clarity. But can I connect to him offline to ask a few questions that I have?
Yeah, sure. You can find me on LinkedIn. I can share my LinkedIn later.
Okay, thanks. Thanks, Luke.
All right.
And any other questions from anyone? I'll put Luke's LinkedIn on the chat as well. Just to let everyone know we're still going. I know a few people have said, oh, I enjoyed that. We've still got a bit more to go.
Yeah, we have a code segment now if people are interested in the nitty gritty. So yeah, I will start with that. So can everyone see my code here?
Yeah, we can see that.
Awesome. So in this code, we will train a sentiment analysis model based on a data set of 50,000 IMDb movie reviews. There are 25,000 positive reviews, 25,000 negative reviews, and they're split across a 50-50 train and test set. So conventionally in Python, we import the libraries we're going to use for our project. So yeah, I guess I can share the code and we can go through the comments at another time. You can go through the comments at another time, but I'll just brush over it. So the most important libraries here are pandas, which is used for kind of storing our data in a usable format. We have NLTK, which is where we find our stop words in our lemmatizer. And then we have some vectorization library within sklearn, which allows us to perform our word embeddings very, very easily. And then we have a random forest model and some metrics, which are also from sklearn. So firstly, we read in the data. There's a certain folder structure to this data where we have a train positive and negative set, and we have a test positive and negative set. So this function basically reads in that information based on this kind of data structure, which it essentially looked for the structure of data that is provided. So I looked at what they gave me and I produced a function that would read that in. That's basically what's happening there. And then we execute the function and we read in the data, and we're left with something like this, where we have a positive train set, negative train set, and positive test set, negative test set. So after that, we basically combine the positive negative train and the positive negative test into a total train set. And then we shuffle that data set. So it's basically not all positive reviews followed by all negative reviews. So we have a bit of irregularity, which helps the model train. And then we would essentially do the same for the test set. So yeah, we concatenate the positive and negative results of the testing. So after the data is read in, we have the word embedding section. So we define our stop words and we define our lemmatizer. And then I just needed to write this little function here. So the lemmatizer ignored stop words because there was a little warning message and I just needed to fix that. So what we do now is we define our preprocessor as the lemmatization function, which I made. And then we define our stop words as the stop words, which are defined within the natural language toolkit library. And then we also specify n-gram range. So this basically means that n-grams can be between the length 1 and 3. So we can have a unigram, a bigram, or a trigram. And it will basically fit the n-gram model to the data. So then after that, now that we've defined our vectorizer, we fit and transform the vectorizer to the train set, and then we transform the test set also with the same vectorizer. And just to kind of reiterate what I was saying about sparse matrices, this data is automatically stored in a sparse matrix format, in a compressed sparse row format, which is more efficient. So conveniently, we can observe there is a problem with storing sparse matrices, but these libraries try to solve that for you, which is nice. So yeah, this model would normally take 11 minutes to train. So I kind of have a pre-trained model, which I trained earlier in the day. So that basically saved us some time, so we don't need to wait around for the model to train. So how the model would be trained if we were to train it, but we won't execute this, would be we just define a random forest classifier, and we have a random state, which basically means every time we train the model, it will train in the same way, so we can fairly compare results. And we also, after the model is defined, we then fit it to the data. So we pass in the train set, and then we tell it out of the train set which things are positive sentiment, which things are negative sentiment. So this is the data, this is the labels. So after that, we have model evaluation. So we can basically look at how good our model performs. So firstly, for model evaluation, we need to predict all the values over the entire test set. And then how we evaluate the model is we compare the predictions against the actual, the ground truth, the actual positive and negative results within the test set. So our first metric conventionally is accuracy score, which is the amount of the proportion of results that are correct. So here we can see that 93% of predictions are correct, which is pretty promising. This is a metric between 0 and 1. So the closer to 1, the better. Then we have precision, which is actually 100%, which is quite impressive for this model. But just to kind of show you that these metrics can provide different information, our recall is only 86% compared to the precision of 100%. So this shows that our model is not perfect, and it does display some level of weakness. And then we have an F1 score, which, as I mentioned before, is a hybrid between precision and recall, and that returns 92.8%. So this basically is showing us that our model is doing quite well. And just as a little bit of fun, I thought I would make a little function that enables us to enter a bit of text, and then our model will make a prediction on whether that's positive or negative. So here I wrote this movie is good, and then this predict sentiment function will pass in the sample text, and then it will return positive sentiment, and then we can say this movie is bad, and it says negative sentiment. And I wanted to give the opportunity for other people to give suggestions as to what I should enter to test our model. So any suggestions?
Put some suggestions in the chat. Just while you're waiting for some ideas, Kriti's asked, how do you know the actual? Is that from the labeled data set? I think she's talking about the scores that you were talking about.
Yeah, so the entire data set is labeled. However, we only expose the model to half of the labeled data when it's training. So the test set is data that's unseen by the model once it's trained. So it doesn't know the labels of the train set. All we can do is compare the results of the predictions on the test set to the actual results of the test set. Does that make sense? So we hold back the test set until the model's already trained.
So we've got a couple of ideas. This movie is not so bad. How would it work with double negative?
This movie is not so bad.
Ah,
So negative, and I have actually explained the reason why this is the way it is. It's because the count vectorizer we're using is a bag of words model, and that does not take into account ordering of words.
Yeah.
So,
Okay.
yeah.
What about this movie is
so
mediocre?
This movie is mediocre. Positive.
Okay. What about this movie is wicked?
Yeah, that's another good example. So that's very context-specific vocabulary.
Ah, it's
Positive.
got that one right. Okay.
Yeah.
This movie is sick. Yeah, it's got it. It's got it.
Those two words we just entered will basically be correct or not based on when the data was retrieved from IMDB, because maybe 50 years ago, the data we would have for movie reviews would not associate those words with good movies. So yeah, that's another factor there.
That's really good. What about this is not a good movie? I think that is. This movie sucks.
This is not a good movie is positive because the drawbacks of bag of words models. This movie
sucks. I think that is all of them. So it's done pretty well, hasn't it?
Yeah.
Yeah, good examples.
Yeah, the interesting thing is we can kind of see the drawbacks of the model. And this is, I mean, people have done a lot of analysis of these results before, and it basically points us in a direction of where we should go with research when we can point out these glaring problems with models. So yeah, a lot of the deep learning is designed to kind of solve these problems I mentioned earlier: negation, domain of application, sentiment, words not expressing sentiment, etc. Okay, so that is my session. I hope you guys enjoyed it. We have some time left for questions if you have any.
Hi, Luke. How to deploy these models? Have you got experience in that?
In model deployment, so model deployment is often done with web servers. So you would spin it up on a virtual machine on Azure, for example, and you would have a server where you would give it REST. You would communicate it through a REST interface, and you would send it things, and it would send things back. So it would basically be sitting there waiting for things to be given to it, and it will run based on what you want it to do. So you would pre-train it, and then it would be sitting there ready. For example, in this case, you give it some text, and it will return the sentiment. And yeah, cloud solutions are often used for that type of thing because they're very fitting.
So what's the user cases for the deployments? What is the user case? So how these deployed algorithms used in the field in real time?
Are you referring to in sentiment analysis?
Yes.
Well, I haven't done too much work in deployment of sentiment analysis applications because it was more of a research topic for me. However, you could have a chat bot, for example, that you could tell it how you think of a movie, and it would return the results automatically of the sentiment. And I guess a more conventional sentiment analysis usage would be for if you wanted to know what people think of your film, separate from the actual star ratings that they provide on IMDb, then you could run a cloud deployed sentiment analysis model over all of the reviews of a given film. And that would basically inform you as to what the crowd thinks of your film. And I suppose in Twitter as well, if you want to know what people think about a certain hashtag, for example, if you're Barack Obama and you want to know what people think of you, then there are many, many tweets people write with hashtag Barack Obama. So you can kind of get a feel for the sentiment and what people think of that topic. those are some applications, but
That's
there are
excellent. Thank you. You got exactly what I'm looking for. Thank you.
Yeah, there's quite a few applications in conversational AI, for example, with customer service chatbots. So that might be used to trigger, or potentially in sales as well, but to trigger when a conversation gets escalated to an advisor. So if somebody's irate, for example. You've got 3 more questions in the chat, Luke. So how can BERT, B-E-R-T, be used to improve existing models?
So BERT is it enables you to train a more powerful word embedding. There are pre-trained BERT models out there, but you can also train your own, although it's not advised unless you have a large data set of potentially over 100,000 documents. So BERT would essentially replace this step here, word embeddings. And it would actually, often you wouldn't need to use like lemmatization and stop word removal. It would actually replace the entire process. So all these kind of traditional methods would be thrown out the window if we use BERT. And then BERT would essentially return a vector, so a series of numbers, which will correspond to either a given document or a given word, with a document being a series of words. And then you would just pass that information into your classifier, and it would train off a new set of numbers that is corresponding to the same set of data.
Thanks. And are there some good out-of-the-box examples to try and test with your own data? And I suppose where could they be found?
Examples of what?
I guess just to generally test out NLP and specifically sentiment analysis.
So if we're referring to data sets, the IMDB sentiment data set is awesome, and I would recommend it. There's also a data set called the 20 News Groups data set that is very well established. There are papers written about it, and I would also recommend that. And I'm sure I could think of more examples, but maybe I'll share those on Slack afterwards if people are interested.
Look, quick question again. You clean the data already, and when we have unclean data, what's the best methods to convert into the clean data? For example, in the first step, you gave 4 different data, 4 different points.
Yeah.
How did you come to that point? Train, pause, train, neg, and then test, pause, test, neg.
So obviously we clean the data depending on what the data is, right? And very fortunately in this example, the data is presented to us in this set of folders. So I can actually show you, this is the data set, the file directly from the internet. So what I'm doing is I'm essentially navigating the file system through Python. And then it's a series of text files within this folder that is all the movie reviews. So this data set is very, very easy to use. However, in other data sets, we would need to clean up certain data. So for example, maybe a common problem would be that some movie reviews would be blank. So what we would need to do is remove blank movie reviews from the data set. Maybe some movie reviews would be unlabeled, so we need to remove those. So yeah, I guess the way we deal with data is adaptive to not only the data we're given, but what we want to do with it. But yeah, the academic data sets are very often very clean. So there are some data sets out there where you can kind of work on them quite quickly, like in this example, and we don't need to fiddle with them too much.
Is there any rule I can apply for this train, pause, and train, neg to separate in my unstructured data or unclean data?
Could you rephrase the question, please?
So I have a data, uncleaned data. Okay. I want to separate, I want to create the for these text files, train, pause, train, neg, and then test, pause, train, test, neg. So to do that, I need to follow some process or best methods. Yes, it's up to the business case, but to separate the data in a full raw data to this level, is there any methods I can apply So I'm just new to this kind of a NLP thing. Just I want to, I know how to clean the data, but I don't know how to set this in the train test methods and pause neg. So
Okay, so this is actually not a completely traditional example I'm giving, because actually already in the folder, they've split the data into train and test. However, in reality, you'll likely receive the whole data set at once. So you will need to perform a process called train test split, where you would essentially randomly split the data into a kind of 70% train set and a 30% test set. And the other part of that is in regards to labels. You would basically you would tell your model to look for things that are dependent on the labels that are provided. So this is positive and negative because the data we've received has only been labeled with positive and negative labels. So in another example, there could actually be many more labels. So there could be like very good, good, mediocre, bad and very bad, or it could be a matter of topics as well. So we could actually be doing a completely different task where we want to identify whether a document is a news article or it's a blog post or it's a social media post or something. So the labels correspond to the task, and often the train test split is something that we have to do, but that will very easily be solved for you with this sklearn library. And there's a function called train test split, which you should look at in regards to splitting the data.
Sure. Based on this split, the question people asked, this movie is not so good. It depends on this file and the term in the true positive or train negative or test negative file. That output is depending on these files. How we split?
Could you rephrase the question, please?
When the people asked this movie is not so good, or
yes.
This movie sucks, it gives the positive, even though it's negative.
Yeah.
Negative. So is that answer depending on these files, how we split that data?
Yes, that's exactly what's happening. So the model will basically try to extrapolate what it has learned through the training set. So the model will only be as smart as the data you give it, essentially. So the reason why it got these answers wrong is because the train set might not have all the relevant examples for the model to fully understand the problem of sentiment analysis, but also another factor is the algorithm, and sometimes the algorithm needs to be very powerful in order to actually understand the concept of negation. So it's partially the data, partially the algorithm as to why some of the predictions are incorrect.
If I enter those words in this negative file, train negative file, will that give me the right answer?
That's a good question, and the answer is probably, but not necessarily, because models are supposed to kind of be generalizable, and they're not supposed to only predict things that they've seen before. They're supposed to kind of build on top of the knowledge that you give them. So it depends on the other examples that the model is given, but potentially if you did expand your training set, then it could make the model more powerful.
Thanks, Luke. And Jay's also had a question. It might be that you've already answered this, but just to clarify, she's asked, does the accuracy depend on the training data set or the library being used?
The accuracy is a bit of both, right? So we need a good training set, but also we need a good algorithm, and we need a good way of performing word embeddings. And I guess the library, in this case, is responsible for the word embeddings and the algorithms. So yeah, there is use cases for using different libraries which support more powerful algorithms. Yeah, but in this example, we've used something that's quite easy to use. And we've trained our model in one line of code here, and we didn't even enter any like special kind of parameters, or we didn't tweak the model at all. We just kind of deployed it as it was. but there's a lot of customization that can be done in general.
That's great, thank you. It sounds like you've answered all the questions. There's a lot of messages on the chat just saying thanks, and there's a lot of great insights that have come through, some great examples here and a fantastic talk. So thank you so much, Luke.